Hello everyone, and welcome to Calculus BC. In today's episode, we're going to be discussing volumes via cross-sections. And where we last left off with volumes was we were taking shapes and rotating them around a particular axis or a particular line. And by doing so, we would create either a bunch of cylinders or a bunch of hollow washers to create a rotational area. Volumes using cross-sections is different in the sense that we're finding volume not by rotating a figure, rather than we are going to be placing little shapes inside the figure, almost like little bricks or hotel buildings or homes, depending on the shape that we're looking at. So the first example I'm going to use is I'm going to use the basic radx function. I'm going to find the volume on 0 to 1. We're going to be perpendicular to the x-axis, and we're going to be using the square shape for it. It's a pretty basic run-of-the-mill problem. Now, if you notice, I drew the coordinate plane a little bit differently. I drew a z-axis here to simulate the notion of this thing being 3D. The x-axis, if you can imagine, is the thing that's sticking out of your screen right now. The y-axis is actually inside the screen. And if I was to graph a root function, it wouldn't grow like this, right? Because that would already be protruding out of the screen. But it's really going to do something more like this. It's going to grow out like that, and then eventually almost go parallel to that x-axis. So if you could imagine the root function doing something like that. And then the squares will be placed inside the shape. So if you can imagine, the first base will be here, right? Yeah, I'm trying to do that, like that, yeah. And then it's going to stick up out of the board like this. Now, obviously, this isn't a perfect square, but that's okay. I think the idea is kind of there. However much its base is, its height is going to be worth that much as well. So hopefully you can imagine that as I get to here, where the base is going to be super, super long, the square is going to be much bigger than it was, like way back here when the square was like really, really small. And so that's going to be how we find our area, where it's just the summation of all of these squares that are sticking up out of the board, and there's going to be a lot of them, right? Because they're going to get infinitely thin, and we're going to do the base times the height times the width, and then we'll find the volume of this weird-looking figure right here. So how do I do this? Well, remember, the shape in question that we're working with is, in fact, the square. And so what is it exactly that determines the volume of a square, or in this case, a cube, right? Because we're going to be making this in 3D. Remember, it's length times width for the area of the square, right? So this would be the length, this would be the width, but because they're identical, we can consider them to be the same. Well, what was it that determined this base length right here? Well, from here, this was the height of the function at that moment in time, so this was going to be f of x, right? Or in this particular case, it would be rad x, which hopefully makes sense that the width would also be the same, right? Because it's a square, so the base and the width would be equal. So I know that a rad x squared is going to be part of my volume process of this problem here. Now from here, the thickness of each square is going to be determined by the space that it takes to get from one square to the next. In other words, what I'm talking about this orange space right here, the space between them. Well, that space right here is traveling along the x-axis. It's traveling along the x-axis every single time. In fact, if I just bypassed a bunch of squares here, that distance right there, right, is traveling parallel along the x-axis. And that distance right there is delta x. Now, as we sum all of these up, as we saw in the last episode with integration, that delta x gets so small that it becomes dx, that infinitely small change in x. And then we finalize this thing with a summation, which was the limit of the Riemann sum. That became the integral on the interval 0 to 1, and it becomes this. So what we have is the integral from 0 to 1 of rad x squared. Again, it's technically rad x times rad x for base times height, and then width was the dx. And so here we go. This is where we're at. So go ahead and just cancel out the squared and square root. And then we can integrate this thing, x squared over 2 on 0 to 1, and I think we kind of know the end of this movie right here, where it's going to be 1 squared over 2 minus 0 squared over 2, which is going to be 1/2. And that would be the cross-sectional volume of this shape on 0 to 1 of this function. So pretty basic. I mean, again, this is kind of a review from AB. I'll do an example here of when it's not a solid figure. And again, solid versus hollow isn't really going to make a difference. We're not rotating anything, so it's not like it's going to be outer radius minus inner radius. But we can take a look at it anyway. Equals x. And then let's go ahead and go perpendicular to the y-axis this time. And again, we'll use squares. So notice how I didn't give you any limits of integration. And I'm actually not going to draw this thing in 3D this time because I really want to make sure that we get these limits of integration down. From here, I'm going to go ahead and actually, you know what? Let me qualify something here. I'll just go and qualify in quadrant 1. That way it doesn't get too confusing. So from here, my line is going to extend up like this, right? That's my line. And so now from here, let's go and find some points of intersection. So I'm going to go ahead and say x cubed equals x. So these are my limits of integration. And so if I look really, really hard, I can tell that x would have to equal 0 or 1. And so those are going to be my limits of integration, so 0 to 1. Now, by the way, I just made a mistake. That shouldn't be x equals 0 to 1. That should be y equals 0 to 1, right? This is a dy integral. And so the way I got that was the coordinates of intersection are 0, 0, and 1, 1. And just to be absolutely clear, I pulled from the y limits of integration. So please make sure that we're being clear about that. Don't make that mistake. Okay, so now from here, I just talked about it being a dy integral. How do I know? It's because it's perpendicular to the y-axis. And so from here, that's a problem, right? I've got to get both of my functions as x equals y functions. So that's going to be x equals cube root of y. And this is going to be x equals y. So these are my two functions here. And since I'm moving perpendicular to the y-axis, it means it's going to be right minus left for the spacing. So in this case, it's going to be curve minus line. So that's going to be cube root of y minus y squared, and then dy. Right? And the reason why it's squared like that is because each of these is based off of cube root of y minus y, cube root of y minus y, like that. So if we had to multiply this thing out, we would get the integral from 0 to 1 of, looks like y to the 1/3 minus y squared dy. And so let's go ahead and just multiply this thing out. So I got 0 to 1 of y to the 1/3 minus y times y to the 1/3 minus y. I would normally shortcut this, but I want to make sure everyone knows exactly what's going on here. Looks like I'm going to have exponents being added, so y to the 2/3 minus y to the, looks like, let's see, 1/3 plus 1 is 4/3, but there is 2 of them. And then looks like plus y squared dy. So that should be a 4 right there. And I'm going to integrate that from 0 to 1. So now what I've got here is I've got y to the 5/3 times 3/5 minus 2, y to the, looks like 7/3 times 3/7 plus y cubed over 3 on the interval from 0 to 1. So let's simplify this out a little bit. It's going to be 3/5 y to the 5/3 minus 6/7 y to the 7/3 plus 1/3 y cubed on 0 to 1. Luckily, anything with 0 on it is going to go away. So really what I'm left with is I'm left with 3/5 times 1 minus 6/7 again times 1 plus 1/3 again times 1. Again, anything with a 0 is going to get left off. There's no real need to go any further than this. We'll just go and leave it right there. So hopefully cross sections make some sense. I'm going to be right back. We're going to go ahead and take care of what it looks like when there are other shapes other than squares. So give me a second. Let me clean the board. All right, so we got a lot of different shapes here that we could be messed with later on going down the chain here. So let's go ahead and figure out how we get each of these. So with the semicircle, I left myself some space here because I'm going to try and extrapolate each one. Try to keep in mind that all of these shapes that I'm giving you are all based off of the square. So the square element will be part of it. So when it comes to a semicircle, we knew that it's going to be the integral of f of x somehow, right? And so that's going to be dx. But how do I reconcile this with a square? Well, from here, remember, the square was the integral of f of x squared dx on the interval from a to b. So how do I get a semicircle out of this? Well, since I'll just go and write the base right here. If I draw a square and I put a semicircle inside of it, right? Put a semicircle inside of it. Well, we remember from the square that the distance from the axis to the function was always f of x or f of y, depending on what kind of integral you were doing. But if I was to do a semicircle, right, that means that now I have to do pi r squared, right? So I know that my radius is equal to 1/2 of f of x, right? And I know that the area of a circle is 1/2 pi and then r squared. So that'll be 1/2 f of x squared, right? So if I simplify him out, I'm going to get 1/2 pi times 1/4 f of x squared. Hey, it's just like the square. So if I just square this dude, multiply the 4 and the 2 to get an 8, that can be a 1/8 on bottom. That pi is also a constant, so that 1 times pi can just become pi. And that is why when it comes to a semicircle, your coefficient that rests on the outside is going to be pi over 8 times a square. So intervals from a to b. Hopefully that makes sense. Isosceles right triangle with a leg as the base. Again, let's try and reconcile this with a square. What is this going to look like? Well, a square is pretty simple. I mean, it's just that, right? We know that the base is f of x. And an isosceles right triangle with the leg as the base, this dude, well, that's an isosceles right triangle right there, right? We got these guys being congruent. And so does it make sense that finding the area of this would be 1/2 of the integral from a to b of f of x squared dx, just like the square, right? Again, base times height divided by 2 is the area of a triangle, or you could just say half of a square. So notice how, again, these are all kind of related to the square, right? The isosceles right triangle with the hypotenuse is the base. Well, again, it's just this, right? And so from here, I'm going to go and make the hypotenuse the base right here. So that means that the triangle is going to look more like that now, with f of x being here. Well, from here, let me go and break this triangle out. And what that gives me is it gives me f of x here. Well, remember, this is a 45, 45, 90 right triangle, right? And so that's going to be f of x over square root of 2, right? F of x over square root of 2, because that's how I move from hypotenuse down to leg. I divide by rad 2. Unlike when we were learning this in integrate 2, we would multiply by rad 2 to get to the hypotenuse. Well, let's take a look at the area of this triangle here. That's going to be 1/2 base times height. So that's going to be f of x over rad 2 squared, right? And so from here, that looks like it's going to be f of x squared. Hey, the square again. Here it comes. It's always back to that square, isn't it? Rad 2 squared is 2 times 2 is 4. So it looks like I'm going to kick that 1/4 out from a to b dx. Another way we could look at this is if you were to split him down, that would be 1/4 of this square. Another way of looking at it if you wanted to. Moving on to the equilateral triangle. So again, go back to the square, right? It goes back to the square. I'm going to go and draw an equilateral triangle inside, and it doesn't quite reach the top. One of the fundamental characteristics of the equilateral triangle is its angular distribution. And so from here, these would all be 60, right? But what else do we know about this equilateral triangle? Is that its base is f of x, right? Its base is f of x. So from here, if I pop him out, I can call the base f of x. I can split him down the middle, making this 60, making this 30, and then now I can pop this guy out again to make half of a 30, 60, 90 right triangle, calling him f of x over 2 with f of x rad 3 all over 2. And so again, what's the area of this triangle? So it's going to be area equals 1/2 base. Now, please bear in mind the base is not going to be f of x over 2. The base is the whole shebang here, right? So it's f of x times the height is going to be f of x times rad 3 over 2. So f of x rad 3 over 2, which ends up becoming rad 3 over 4. Again, here we go with the square again. F of x squared dx integral from a to b. The rectangle is pretty easy, actually. And I apologize, I didn't space myself out correctly on this one, but the rectangle is pretty easy. This would just be f of x times g of x. Right, so if this is f of x, g of x, sometimes they'll just give you a problem. They'll say, hey, the rectangles whose height is based off of the function y equals natural log of x or something like that. This would just be from a to b, f of x times g of x dx. Base times height times width. So hopefully that makes sense to you. Those will be the coefficients that you guys will need to know if you're going to be doing an other shape than a square. But remember, it always kind of relates back to the square. So that should take care of cross sections for you. I apologize, it was a bit of a short lesson, but it is review, and so we will do more examples in class, and I will see you all in the next episode. Please leave comments or questions in the comments area. See ya.